you can actually show that there are ways of doing that in such a way that between collision, the sample and microcanonical ensemble, and also overall, you may end up, the canonical ensemble is sample. And this is, there are several algorithms to do that, some of them very, very recent, proposed in the literature. The only message that I want to give you here is that this is a way that one may want to use, and that is used these days also in the within first principle molecular dynamics to actually change the temperature of your system. So another variable that you may want to control in many instances is actually the pressure of your system, and there are algorithms and that have been devised very similar in spirit to the one that I told you about in the case of the temperature. So one is again a Berenson scheme where instead of having the system in contact with a heat bath, you have the system in contact with a pressure bath. And then if you want to change the pressure of your system, which means you want to actually doing so by changing the volume of your simulation cell, you exponentially scale the volume of your box by a certain factor. So you see, very much in the same spirit as we did with the temperature. You actually have a target pressure, a pressure of your bath, as you did have a target temperature, and then a time. This is just a coupling constant, which tells you how long it will take during your simulation to bring your system at a certain pressure. And this is another parameter which is related to the isothermal compressibility of your system, that you don't compute, actually you fix or you use and you take as input from what you know from the system to scale the volume and to compute the pressure. This is the expression of the pressure that you have when you actually have and use empirical potential. So there you have a kinetic part, which is just rho kBt, where rho is the density, and the potential part, which is coordinates times force. This is an expression you can use if you have a classical system. Okay? If you do a first principle calculation, this expression may not be used as it is anymore, because you have a wave function entering. You have your electronic states, you have a wave function. Wave function has a normalization factor in front of it, which is 1 over square root of the volume, and this is not the expression you should be using. This is just a warning. So this is not a completely general expression. This is applicable as an expression of the pressure when you have an empirical potential. That's the warning, so that you not take this and use it in the first principle molecular dynamics course. It will not work. But anyway, that's not really the point here. The point here, you may want to fix the pressure of your system, and one very simple way of doing so is rescaling the volume of your simulation cell in the same spirit and as we talked about rescaling the velocities to take the system to a certain temperature. And the equivalent of the Noether thermostat to keep the pressure constant is the so-called Anderson barostat. Anderson, of course, is the person who came up with the idea. And the same kind of philosophy is applied here that is behind the Noether thermostat. You add an additional degree of freedom to your system, which in this case is the piston that you want to use to act on your system to change the volume, right? And again, same as for the Noether thermostat, you have a system, you redefine your model system, which is composed by your atomic coordinates and the additional variable. You associate a kinetic and the potential energy to your new variable, and again, you have a coupling constant. This is called Q again, but it's not the same Q as before, right? It's not the same Q that you use to actually change the temperature. It's another coupling between the reservoir and the system, and with the same kind of property than before. In some of the paper that followed the original paper, where the formalism was presented, Anderson actually showed that the time average of the trajectory that are derived using this thermostat equals the isoenthalpic isobaric ensemble to order 1 over n squared. So you are actually sampling the isoenthalpic and isobaric ensemble by using this thermostat. This is not true if you use this one. Okay? The simple rescaling of volume, as in the case of simple rescaling of velocities, doesn't sample any statistical ensemble. And of course, and let me not go through this again because I want to cover some of the example at the end, but there are ways of coupling the constant temperature and constant pressure formulation that I just told you about, the Nose and the Anderson, to come up with a formalism to carry out constant temperature and constant pressure molecular dynamics. There are several formulations that have been proposed in the literature. One is the Hoover formulation, where you write down an equation for your velocities. So this is the derivative, so this is your acceleration equal to the force, of course, and then there are scaled momenta, and one scaling takes care of the scaling of the volume, one parameter, and the other of the temperature. But these equations are not as trivial as I made it sound right now. To derive them and to see that really you can have constant temperature and pressure by sampling the correct ensemble, one needs to write those down and convince himself or herself that this is really true. I'm just writing down these equations to give you an idea that this can be done, not to prove that these equations are sampling the right ensemble. Okay, so let me summarize this part. So you can fix the temperature by scaling the velocities, changing some or all of the velocity, for example, by randomly selecting a member, changing some of all the velocity and setting it to a randomly selected member of the Maxwell-Boltzmann distribution, coupling the system to the heat bath. You can do analogous methods to choose and maintain the constant pressure, and you can combine these two methods. Okay? Now, which one would you want to choose? I said this many times. The scaling, both of velocities and volume, is simple, very easy. Convergence, meaning equilibration, may be a problem. Okay? Usually, people use this for initial phase. So, for example, you have a solid, you want to melt your solid, and you want to start having your atom move and acquiring some kinetic energy. This is a good thing to do. You don't have to worry too much about which ensemble you will sample, because the initial equilibration phase is thrown away anyways in UMD. So the part of the simulation that you actually do to bring your system to equilibrium, it's not reused to compute thermodynamic properties, and so it doesn't really matter the way you bring your system at equilibrium, and you can do scaling, for example. Stochastic approaches, again, there is actually a lot of very, very recent literature. This is very much a topic of research. Are usually more stable than scaling. You have a method which is no longer deterministic. We talked extensively about the Nose. Again, warning. When you actually couple your system to a thermostat or to a barostat, your dynamical properties may not be correct. This doesn't mean that you will not find a lot of paper in the literature computing dynamical properties with system with thermostat or barostat applied and without worrying too much about it. But you should worry. You should worry because dynamical properties may be a real problem even if your thermodynamic properties may be completely fine. The last thing I want to mention, and that it has been mentioned already actually in the lecture by Stefano De Gironcoli last week, is that you may do a molecular dynamic simulation where you do not only vary the volume of your cell, but you also vary the shape. And this has been invented by Cardinello and Raman at the beginning of the 80s. Almost always, in this case, it's fair to say that the dynamics is unrealistic, and especially in the case of a simulation of fluids, liquids, physical cell shapes may be obtained. And so it is very important to exercise a lot of care when applying this method. However, it is extremely useful to study, for example, transition between crystal structures and to study phase transition, which are accompanied by differences in transition in crystal structure. And I just copied here one of the viewers that actually Stefano De Gironcoli showed to you during the first week when he was talking about variable cell shape and molecular dynamics. So I think that he told you also some of the specific algorithms that also are implemented in quantum espresso to do variable cell minimization, structural optimization, and also molecular dynamics. For systems which are solids and for systems for which you know the phase transition that you're studying, the initial cell structure and the final cell structure, this is a very powerful tool. If you are liquids involved or if you don't know your system very well, a lot of care must be exercised because there are instabilities that can arise actually all over the place. Okay, so now we know everything. We know potential, size of the simulation cell, we know how to choose the algorithm, and we know how, at least we know that we have to worry about the statistical ensemble to choose, and we have to worry about the way that we actually keep the system constant temperature or pressure depending on the properties that we want to compute. And so this is our MD loop. So we computed the forces, we solved the Newton equation, and we store the information that we may want to reuse, like coordinate velocities, and we repeat this for many, many steps. So how long? How many steps? And how long is it meaningful to run a simulation for? And there is, of course, no general answer, and it is as long as it takes for the quantity of interest not to change anymore in a statistical sense as a function of time. And in a statistical sense means within desired error bars. Never forget that molecular dynamics like Monte Carlo and the results are only meaningful when you specify the error bars that you have associated to your results. No error bars, no meaningful results. Okay? Zillions of papers published in the literature without any error bars. But no error bars, no meaningful results when you're using these. These are statistical methods. It's not just doing a minimization of your density function and getting a number that you get at the end. Of course, it has error bars as well, but no statistical error bars. Here, you have to specify your error bars. So let me just briefly talk about this. I will tell you about a very general concept, but I want to make sure that everybody here gets the message that when you use MD, you're trying to do statistical predictions, right? And first of all, as the trajectory of any system that you will simulate is very sensitive to the initial condition. This means that you start your simulation and from initial conditions that are very close, and if the system is ergodic, your trajectory will diverge, okay? So shall we all go home and cry and be very sad about that? Actually, no. This is not a real problem because we are not interested precisely to know what happens at a given time. We are using the trajectories to compute statistical averages that then, if the system is ergodic, we can identify with thermodynamic averages. So this is no problem. So we can start from different initial conditions. Our trajectory will diverge, but it doesn't matter if we perform a simulation correctly from a technical point of view and we take the averages correctly on a simulation time which is long enough, we will have actually meaningful results. So results are numbers. And so these are numbers that we have to interpret, just like experimentalists have to interpret their numbers, their data. They are obtained for finite systems, always. Especially for disorderous systems, this is something that we should check carefully. And by checking carefully, meaning that in principle, we should be doing finite size scaling to understand whether our results are meaningful or not. Not always. We are actually, in many instances, we cannot do finite size scaling really by doing simulation on different sizes, and we have to come up with different ways of checking the robustness of our results, but this is certainly something to keep in mind. And even if our simulation were free of approximation, perfect potential, we have done finite size scaling, the results are affected by systematic and statistical errors that we have to estimate, right? So, statistical errors. And this is just like in an experiment. Actually, MD and Monte Carlo simulations are very similar in spirit to doing an experiment. You have to interpret your results, you have to put error bars, and in many instances, once you have done a simulation and you have gotten numbers for your thermodynamic properties or even dynamical properties, if you are careful, you will have to do something else to interpret your numbers, right? Statistical errors, they affect all simulation, just they affect experiments, and this is because a simulation or an experiment takes a finite time. No infinite simulations, of course. Then you have systematic errors. Systematic errors, experimentally, they are associated with lack of calibration or incomplete calibration. I wouldn't be able to speak too much to it, but in a computer simulation, there are several types of systematic error. I said already, finite size of the simulation. Finite time step. This also affects how good your conservation of energy, for example, is, and ultimately how good your numbers for statistical averages are. And of course, there are round of errors that are always due to the finite precision of the machine that you use. Every time you have a quantity, you have to give a quantity with its error bar. And I want just to say for the 10th time, it's very important, simulation results are not meaningful without an associated error bar. Let me so the very first thing that one has to do before actually assigning error bars to the computed data is to understand what is the set of data that you use out of your simulation representing your system at equilibrium. So you do a simulation, for example, again, and you start at a temperature 0. You want to go at finite temperature, and there is an amount of simulation data that you collect that you compute to bring the system from a temperature 0 to a temperature T1. And then you want to simulate your system at a temperature T1. All the first amount of data that you generated to bring your system at a certain temperature and certain pressure do not represent the system at equilibrium, and so they should be, and they will be discarded to compute temporal averages, right? And so how much data you discard is a very important question that you always have to ask yourself, and of course, you want to discard as few data as you possibly can, but not but you still want to do meaningful calculations. So this is a difficult choice, and one needs to check this very, very carefully. So usually we just take a very poor man approach to understand how many data to discard, and so you compute averages by discarding an increasing number of initial data, and you see when your averages don't change anymore. Okay? It's not very elegant, it's not a particularly, it's a very straightforward way of doing things, but this is what we do in most of our simulation. So these are just, I'm sure everybody knows that, a review of how we put error bars on our data. We all know how averages are computed by just summing the instantaneous values of our quantity and dividing by the number of time steps or the number of moves if you had a Monte Carlo simulation, and then we can estimate the statistical error in the usual way. And I'm just reminding you of the formula here that we use to look at standard deviation of a certain quantity. Now, of course, these formula that we all use to attach error bars to our data are only true if the data are drawn from a Gaussian probability distribution and data are uncorrelated. Now, correlation of data is may be actually a real problem. I will show you an example of that, specific example later on. One of the most common ways of actually looking at correlation of data is doing what is called blocking or reblocking transformation. And again, this is a very simple concept where you actually, your data set is divided into subset, and averages are actually computed over subset sets, and statistical error are recomputed all the time until you reach an average over subset that doesn't change as a function of time. This specific reblocking transformation was, for example, introduced in this paper about 20 years ago. Okay, it is interesting actually that if you look at the papers about molecular dynamics and the Monte Carlo simulation, people doing the Monte Carlo simulation, for some reason that I don't quite know, but have been much, much more concerned about error bars, about the analysis of results than people doing molecular dynamics. Probably because in Monte Carlo sometimes data correlation is more severe. Actually, I don't quite know, but if you look at the paper and the literature, Monte Carlo simulation are almost always given with error bars on data. Many molecular dynamics simulations are not. I don't know why, but you may observe this if you look at the literature. So you do a molecular dynamics simulation, and to any quantity you attach error bars, and then you are actually quite ready to analyze data and to compute your statistical averages. So I want to give you examples of the properties that you can compute by doing a molecular dynamics simulation. And these are very simple examples that almost everybody, of quantities that almost everybody has to compute before computing anything else when you do a simulation, for example, of a disorderous system. So this is a pair distribution function, a auto-diffusion coefficient, for example, for a liquid. And then I will really very briefly mention also the use of MD to actually minimize complex potential energy surfaces. But I will concentrate on these two examples. And in the exercises that, especially those that you will see tomorrow about the molecular dynamics, you will compute partial correlation function for a liquid yourself, and you will also Francois, they will also compute the diffusion coefficients, right? Or at the very end for liquid silicon. So I choose these examples because they are simple, because we can actually get to compute those in the labs. And also because if especially you simulate a disorderous system, basically this is what you will do in a molecular dynamic simulation before doing anything else. So the per distribution function basically tells you on average how atoms are distributed in your system, right? And the partial distribution function, the per distribution function, which is given as a function of distance, is a measure of the probability of finding any two particles at a given physical distance in a certain system. And it's usually used to characterize the structure of a system in a liquid, in an amorphous system. This is the definition in terms of the probability, and this is the normalization that we use to define the partial correlation function. So this is the shape of a partial per distribution function. Usually have a first peak, which tells you the distribution of the first neighbors when you sit on a particle and you look around. And then you get to a minimum, and then you have the second neighbor's peak, and so on and so forth. And then when you go at very, very large distances, of course, the probability of finding a particle close to a given one is 1, right? So this is the width of this peak will depend on the temperature of the system. As the temperature goes down, this peak becomes more pronounced in any typical system, and this minimum becomes low here. Okay? So if you have a system which contains different species and different components, this is aluminum oxide, of course you can draw correlation function for the different species. Here you have the oxygen one, the aluminum one, and the oxygen-aluminum one, where you have first neighbors are here between aluminum and oxygen. And they are the most basic function used to describe the structure of any system that you may want to simulate. So when you want to interpret your results, and for example, you want to know exactly, here you say, okay, I want to know exactly the maximum of my correlation function at what distance it is, and I want to give an exact number of the first neighbor distance. Well, be careful to actually put error bars, also because of correlation of data on your simulation. This is the results of an oxygen-oxygen correlation function for a classical simulation of water done with a classical potential. This tip 5p is just the name of a classical potential. And these are data where we actually have put error bars due to the correlation of data that you have, because your simulation is not very long. And as you see, these error bars actually, especially around the first minimum, are quite significant. So here you cannot really tell with extreme precision the position of your maximum. You can, but still you have to qualify the position of your maximum plus or minus a certain number of angstrom depending on the error bar that you put there. And these are just error bars depending on how long you simulate and how your data are correlated. And it's very important to keep this in mind when you want to give exact peak position of your geobar. Now, let me make one observation here, which is actually a general observation that we should all keep in mind when we compare with experiment. And this happens not only for geobar, but in many instances. In a molecular dynamic simulation, if you want to characterize the structure of your system, of your liquid, of your amorphous, whatnot, you compute geovar, the per distribution function that I just told you about. Then you compare with experiment. Experiments do not measure geovar. Okay? Experiment actually measure structure factors. So for example, if you want to probe a liquid or an amorphous, you may probe the system either with neutron or X-ray. This is the probes for the structure that are typically used. And then, so you actually send your X-ray or neutron with a certain wave vector on your system. You look at the scattered cross-section, and then you define your scattered cross-section here in terms of a structure factor. Okay? So these are the diffraction lengths, for example, of your neutron of X-ray. The exact formula is not very important. What actually is important to retain is that you measure a scattering cross-section which is related through certain scattering length of your probe to the structure factor of your system. And the structure factor is expressed as a linear combination of the partial structure factor. This indicates the different species of my system, with different weighting factors depending whether you have neutrons or X-rays. So you do an experiment to probe the structure of your system, and what you measure is a cross-section which is related by a formula which is quite simple to the structure factor. And this is a weighted sum, and the weighting factor depends on whether you have neutrons or X-ray. Now, so your G of R is related, your pair distribution function is related to your structure factor through a Fourier transform. Okay? So experiment, measure this, and you compute this. So why do I say all this? Just to point out that actually the comparison with experiment for any structural properties of any liquid is a very, very delicate matter. There is no one-to-one comparison. You, with the best possible simulation, you get the partial distribution function, and then the experiment gives you this partial structure factor, and to reconstruct the total structure factor, you need to know whether the experiment is done with neutron or X-ray, and then your comparison is affected by all sorts of uncertainties entering the calculation of this Fourier transform, which, of course, they never measure this for any value of Q, but only for a finite number of Q, so the comparison is actually difficult. And this has to be kept in mind. So when you read a paper and about a liquid or an amorphous or whatnot, and they tell you that the pair distribution function is an excellent agreement with experiment, always ask yourself, what does excellent agreement with experiment mean? Is this a Newton experiment? Is this an X-ray experiment? Did they take into account the fact that actually there are so many uncertainties in comparing with experiments? Because, for example, if I really want to obtain my full structure factor, I do need to know whether the weighting factor comes from neutron or from X-ray. And how is the comparison done here? How did they do this Fourier transform? I mean, they don't have the whole value of Q's, they have only finite Q's. So even for the simplest possible quantity that you may want to compute, which is of course very important to compute because it gives you a description of the structure of your system, the comparison with experiment is very, very far from trivial. Okay? So question then is, why don't I compute S of Q directly? And why do I bother to compute all this G of R? Well, you could, and actually, of course, this is done. But in the simulation, the direct computation of S of Q is affected usually by large errors due to the finite size of your cell. The smallest Q that you have in your cell, because of the dimension of your cell, is usually quite large. And you never describe very well in the simulation the behavior of S of Q for Q going to 0. So it's a non-trivial operation. That's anyway, you will compute this for silicon in your exercise. And here I've just put examples of structure factors just to give you an idea of how they look like. Usually when you have a structure factor, you have a very broad first peak or for double peak and then oscillations, and then here is S of Q minus 1. Your function goes to 0. This is water done with X-rays and neutrons. And you see, depending on the probe that you use, for example, for a system like water, how different actually your structure factors look like. They are totally different, right, because of the probe that you're using. And this is another example of a system which is an amorphous, much more structured structure factor than in the case of a liquid where the system is diffusing. And again, these are just pictures for you to have a look if you want. There are zillions in the literature to give you an idea of how a structure factor of a liquid look like and how different it may look like depending on the probe that you use actually to sample the structure of the system. Okay, so before I go on and I tell you about the diffusion coefficient, any question here? I really want to, make sure that everybody's clear, not about the details, but about the fact that every time you have a disordered system for the structure, even if you have a super accurate simulation, the comparison with experiment is not a one-to-one comparison and it's difficult to do actually. So every time, this is true in general, you read excellent agreement with experiment, ask yourself what does excellent mean, which experiment, what did they do to get that excellent agreement. Okay, any questions here? Okay, so other properties that you may get from molecular dynamics are transport properties. And I've written down here the equations for mass transport, from which we will discuss the self-diffusion coefficient of the system, energy transport, for example, heat flow in the system, and momentum. This is just a fancy way, actually, to express Newton law. So-called Fourier law is the law telling you for small temperature gradients how heat flow through a system with a constant of proportionality, which is the thermal conductivity, and this is Fick's law for mass transport. So let's actually consider just the self-diffusion coefficient. So we have a liquid, for example, molecules in water or argon, and our atoms move, and we want to compute the self-diffusion coefficient. So what's the self-diffusion coefficient? How do we express it? Let's consider a mass current where the initial configuration is just given as a delta function. And let's combine this mass equation here. This is how mass in my system varies as a function of mass, meaning the distribution of particles, right, in my system as a function of distance and time. And let's combine this equation with the law that I call just in a phenomenological way Fick's law here. Okay, so the current and the gradient of the concentration of particle of the mass are related by a constant of proportionality, which is the diffusion coefficient of the system. And I want to express this diffusion coefficient in terms of the mean square displacement of the atoms in the system. So what do? I solve this equation here by assuming that as initial condition I have a delta function. So if I do this, I actually find an expression for my unknown here in my equation, which has an exponential behavior. And the small d, so the capital D is my diffusion coefficient that I'm trying to determine, and the small d here is just the dimensionality of my system. Okay? So to cut a very kind of long story short here, I know how my displacement of the atom, mean square displacement, is related to the mass distribution of particle in the system. I found the solution of the differential equation telling me how this varies as a function of space and time. I combine these two and I find a relationship between mean square displacement and diffusion coefficient. This is also called Einstein relation that you can also derive in a much more phenomenological way. So in your molecular dynamics, so the mean square displacement of the atoms, R square mean, is actually related to the diffusion coefficient by this very, very simple relationship. In a 3D system, this is 6. So mean square displacement is 6 times the diffusion times the time. So how do I compute the diffusion coefficient in a molecular dynamics simulation? I look at the mean square displacement of my atoms, which I just compute as a sum divided by the total number of atoms. I follow the mean square displacement as a function of time, and the slope, modulo factor of 6 here, gives me my diffusion coefficient. So as long as you have the coordinates of your system, you follow them as a function of time, you have a very, very easy way of getting your diffusion coefficient. In principle. Now I tell you in practice what you have to be careful about. Actually, I'll get back to that. Let me tell you right away. This is a calculation of a diffusion coefficient by using that simple method that I just told you about. You look at your mean square displacement as a function of time for water. Again, small system, empirical potential. And this is the determination of the diffusion coefficient computed over different lengths of simulation. So here you simulate for 5 picoseconds, 10 picoseconds, 30 picoseconds. And then you do your measurements just by looking at this slope. You see how difficult this quantity is to converge. So these are 10 to the minus 5 centimeters square per second. And you see, if you simulate for 5 picoseconds or so, you have a value which is almost twice as the one that you find if you simulate for 30 picoseconds. Actually, it turns out that if you really want to converge this number, you have to go to a much longer simulation time than even 30. In this case, you will get the same result as 30, but usually to really have this quantity flat, you have to go to very, very large simulation time. So now, it just so happens that the experimental result is here. So if you do your simulation, you stop here, you declare victory, right? You say, look, I'm really good. I got the experimental results, end of the simulation. So never do that, of course. It's not because your simulation is in agreement with the experiment that it means that your simulation is converged or meaningful. And of course, we all know that, but we all forget that, right? So never stop a simulation because you find a result which is in agreement with the experiment. The agreement with the experiment may be completely fortuitous, and in this case, it would be. This is the experimental value, but if you keep converging your simulation, actually you get to another value. This is important. And you need at least a 30 picosecond for this liquid here. This is not in general. Actually, for liquid silicon, which diffuses much faster, there is a difference of 1 order of magnitude at least with respect to water. You don't need as many picoseconds. But I mean, for water, you need at least 30 picoseconds to converge your diffusion coefficient. But you would need not even 10 to actually converge your partial correlation function. So when we actually ask the question, is the simulation converged, we always have to ask for which quantity, right? So that's So you can compute the diffusion coefficient just by looking at the slope of your R square here, as I said, or as is the case for also other transport property, you may actually compute your cell diffusion coefficient by the velocity autocorrelation function down here. So of course at the position, you can write the position as an integral of the velocity, and then you can use this expression to evaluate your R square. If you do that, and this is just totally trivial algebra, you actually may relate your diffusion coefficient, capital D here, to the velocity autocorrelation function. And this is a general expression that you may write also for other coefficients. So the diffusion coefficient, self-diffusion, is related to the velocity autocorrelation function. Likewise, you can do exactly the same thing and find that the viscosity of the system can be expressed as a stress tensor correlation function, and your conductivity is a heat flux correlation function. If you have a simple pairwise potential, you can actually, in this case here, express your stress and your heat flux in a simple way in terms of your pairwise potential. If you have a first principle potential, these expressions are not valid anymore, of course. They would be much more complex. So, so three messages here, and the message is one, that we can, with the molecular dynamics simulation, not only compute the thermodynamic properties, but also to compute the transport properties. And I've shown you an example of the simplest one, the self-diffusion coefficient. You may express your diffusion coefficient as velocity autocorrelation function, or just compute it as the slope of the mean square displacement. The plot that I've shown here is representative of the fact that almost always converging transport properties is much more demanding than converging static property in molecular dynamics simulation, and in some cases even more demanding than converging thermodynamic properties. Final message, never stop the simulation and declare that your simulation is converged or meaningful by comparing results with experiment. Actually, by doing this, you may well be fooled in many instances. Okay. Before I finally go to molecular dynamics, although I will not give you any technical detail, I want to mention one thing, because if you go out there and you read papers about molecular dynamics, it's useful to know. Everything I said so far is actually about equilibrium molecular dynamics, meaning that we want to simulate a system and have the system reach equilibrium and simulate equilibrium property. There are other techniques that have been developed and actually used quite a bit, especially to compute transport properties, where actually the system is simulated out of equilibrium. These techniques are called non-equilibrium molecular dynamics, and they have been devised in particular to compute, as I said, transport properties. So here is the idea. The idea is that you may actually apply a certain force to your system and look at how the system goes to equilibrium when your force progressively is set at zero. Well, what I mean is the following. For example, suppose that you want to compute the heat flow in your system, and for example through a nanowires. What you can do is to do equilibrium molecular dynamics, everything I said in the last hours, or you can actually apply a temperature gradient to your system. This is the type of force that you would apply if you were to compute heat flow so that you make your system hot on one side and cold on the other side. And then actually you look your system reaching equilibrium. And you look at your system, you look at the way your system reaches equilibrium rather than studying the equilibrium properties of your system. And then in order to find the equilibrium property, you do a limit for long simulation times and for your temperature gradient on your force going to zero. I mean, in order to actually believe that this limiting procedure really gives you a meaningful value for your quantity that you want to compute takes some, going through a number of mathematical equations that I'm not presenting here. Here, I just wanted to give you the concept and tell you there are properties that people compute not by using molecular dynamics, which is most of what I talked about here, but by using non-equilibrium molecular dynamics and by looking at not at what the system does in equilibrium, but looking at how the system reaches equilibrium as a force is actually imposed on the system. So just that you have an idea that there is this technique out there. So if you read paper and if you see formula used to compute properties by using non-equilibrium molecular dynamics, you should know that they are different from what I've been talking about here. I've been mostly talking about equilibrium molecular dynamics. Okay, let me actually skip this, otherwise we'll not get to the examples that I really want to do, because you will start doing ab initio molecular dynamics this afternoon. Okay, so let me go back finally to what we want to do, which is apply all the technique that we talked about, compute geobars, compute cell diffusion coefficient, compute thermodynamic properties, but with the potential which is derived from density functional theory. Okay, so you had a week in good company of density functional theory like last week, and you have been told how could you compute properties and energies and forces using density functional theory, and in particular using the quantum espresso packages. And you also have had two very important concepts introduced. One, we are working within the Born-Oppenheimer approximation, and we have a way using the Hellman-Feynman theorem to actually compute forces from density functional theory. And in particular, if you go back to Shobana Narashiman's lecture, she actually covered the Hellman-Feynman theorem, and she told you, this is from her lectures, how to compute a force acting on a certain atom or on a certain ion in your MD simulation now by taking the average value of the derivative of the energy of the Hamiltonian with respect to the atomic position. Okay? So we have a theory which is density functional theory within different approximation that we can use to compute total energies, and you can use to compute forces, and this is all we need to do our molecular dynamics simulation, right? So now we can do an ab initio molecular dynamics simulation. So we, for example, want to go from a solid to a liquid. We want to melt the system, and we want to integrate our Newton equation of motion that we've talked about for 2 hours now. And we derive the potential from density functional theory. And what do I mean by that? The most straightforward way of doing that is at each step, you solve the Kohn-Sham equation, which, as we know now, of course, are a set of n-coupled nonlinear differential equations, right? And we do this using all the iterative algorithm that you have discussed last week. You can do this for a variety of problems. You may want to melt your system, like here, go to a solid to a liquid, but you can also look at very different problems. Like here is a problem where we look at actually growth of a carbon nanotube on an iron catalyst, and we watch actually the carbon nanotube grow. Dynamics not very meaningful and very short because of the limitation of our simulation, but still giving you hints and quite a bit of understanding to what happens to your nanostructures. So the reason why I'm presenting these two different, one is melting of a solid, the other is a nanostructure, two very different examples, is to convey right away the idea that this is a very general method, because you have not fitted any potential. The generality of the method that you have actually is quite powerful. These are the equation, the Kohn-Sham equation that you have seen many times. And I want to remind you, these are solved iteratively. I want to remind you something that has been discussed yesterday in the discussion. The cost of solving this equation actually grows as the third power the number of electrons in your system. So it is actually, it's a scaling which is much better of most of quantum chemistry method. Already Hartree-Fock scales at the fourth power of the number of electrons, but actually it's certainly the rate limiting factor of any molecular dynamics simulation that you do with ab initio forces, because this is actually a scaling which is not great, of course. So basically, if you double the size of your system, within a certain number of atom range, you are almost at a factor of 10 in computer time per step. Okay, so how to implement Born-Oppenheimer molecular dynamics, and about the other way to do molecular dynamics historically, the first one, Carparinello, and how to implement this in large-scale calculation will be dealt with tomorrow and will be presented by Professor Gigi tomorrow. So today, in the rest of the time, and actually I have to speed up, otherwise I'm not getting there, but in the rest of the time, what I'm telling you is about examples. Hopefully, stimulating your interest in doing this simulation. Examples of problems that one may solve by doing molecular dynamics simulation. So examples, although there are a lot of technical details that will be explained to you tomorrow, just think that you do a molecular dynamics simulation and you actually start from you want to sample a certain potential energy surface, you start from your electrons, and you minimize your electron in such a way that you determine a point on your Born-Oppenheimer surface, then you move your atom. The electrons, once you have moved your atom, are not in the ground state anymore. You minimize them, get them to the ground state, and so on and so forth. This is what we call